So in the last video, we saw how containers help us to run multiple apps on a single physical or virtual machine in their own isolated space without interfering with each other. With a couple of Docker commands, we were able to create images and run containers. Since the world is slowly moving to the cloud, our apps also need to be native to cloud. They need to be scalable and highly available. For example, I have a web app deployed in a Docker container. Now the load on the app increases during peak business hours. As a result, the container becomes slow and even crashes sometimes. To solve this issue, I would have to spin up a new container and balance the load across the two containers. Sometimes this won't be sufficient, so we would have to spin up even more containers. And when the load goes down, we can spin down the extra containers and claim the resources. But how do we scale these containers dynamically based on certain thresholds? Well, we can run Docker commands and spin up containers, but that isn't practical. We want an application or a service that can automate this spinning up and spinning down the containers based on certain defined parameters. And Kubernetes is one such service that helps us manage the containers. And that is why we need Kubernetes. When we talk about Kubernetes, we are dealing with cluster of physical or virtual machines. In this cluster, some machines behave as leaders, also known as controllers or masters, and some behave as followers, also known as workers or slaves. More about leaders and followers in the next slides. Now, there are multiple flavors of Kubernetes available. We can choose to create Kubernetes cluster from scratch. So basically you provision all the required servers which can behave as controllers and workers, and then install all the components of Kubernetes on your own. Otherwise, if you do not want to go through the hassle of provisioning servers and doing all this stuff, you can basically use managed services from popular cloud providers like Amazon's Elastic Kubernetes Service, Google's Google Kubernetes Engine, and Azure Kubernetes Services. And there could be many others in the market as well. But if you want your Kubernetes cluster to be on premise, you can provision the servers, but you want someone to install all the components for you. In that case, you can go with packaged services like Gravity, Rancher, etc. And Minikube is a good example of such package service that can be deployed on premise. But remember, Minikube is only for demo purpose, not for production purpose. So let's talk about the leader, also known as controller or master node. There can be one or multiple controller nodes in a Kubernetes cluster. There are multiple components that form the controller node. Since the job of these components is to control other nodes, they are said to be the part of the control plane. So what are the different components that create the controller node? Let's start with the etcd cluster. This is a key value based database that stores details about pods, replicas, configuration, nodes, etc. Any change to the Kubernetes cluster, like spinning up a new container, stopping a container, adding new nodes to the cluster, is considered complete only if the details related to these changes are persisted to the etcd cluster successfully. Next up is the node controller. A node is basically a physical or a virtual machine that is part of the cluster. The job of the node controller is to manage the addition or removal of the node to or from the cluster, checking the health of the nodes, keeping track of the resources being utilized are also the activities performed by the node controller. Next is the replication controller. This is quite similar to the node controller, it's just that its job is to manage the replicas of a particular container. Now both the components together get clubbed and are managed by the help of a controller manager. And the last one is the kube scheduler. So whenever the containers are supposed to be deployed on the worker nodes, in such cases, this task is taken up by the kube scheduler. So kube scheduler basically tracks the taints and tolerations on a worker node, and based on those details, it will schedule the containers to run on a particular worker. Now, all of these components together are managed by the Kube API server. And this API server exposes a set of APIs using which we can manage the Kubernetes cluster. So basically, whenever we run any kubectl commands, all are facilitated by the help of the Kube API server. Now let's move our focus towards the follower, also known as worker or the slave nodes. The job of this node is to run our containerized applications. Since this node performs activities required to run our application, it's considered to be a part of the runtime plane. The worker nodes have two main components, that is the kubelet and the kubeproxy. Kubelet is basically an agent that gets command from the control plane components. For example, if the kube scheduler wants to spin up a container on the worker node, it would route its request through the Kube API server, and then a kubelet on a specific worker node would deploy the container. Similarly, metrics related to containers running on the worker nodes are also sent via the Kube API to the Kube API server via the kubelet. Now, this kubelet can also be present on the controller node because all other components of the controller nodes like HCD, uh, node controller, replication controller are can be deployed in the form of containers, and to manage them a kubelet is also required. So a kubelet can also be present on the controller node. The next component is kubeproxy. If an app on node 1 wants to communicate with app on node 2, this communication has to be facilitated by the kubeproxy service. So that's the high level overview of the Kubernetes cluster. Now let's understand the basic terminologies used in Kubernetes. Let's start with pod. So if you're familiar with Java, you might have observed that all the methods and member variables are encapsulated within a class. It's only using a class an object can be created and the methods can be executed. Same is the case with Kubernetes. A Docker container cannot be managed directly in the Kubernetes cluster. It has to be encapsulated within a pod so that it can be managed by Kubernetes. Pod is the smallest possible object that can be created in Kubernetes. A container in a Kubernetes cluster cannot exist without pod. So this is the final representation. A container is encapsulated in a pod and a pod is encapsulated in a node. Now this node can be controller or the worker node. Normally a pod always has only one container, but exceptions are already there. So in some cases there could be situations when a pod will have multiple containers, and this additional container could be a helper container. Let's take an example of the mule applications that are deployed to RTF. So a single pod for a mule application will have uh, at least two containers, one for the app and the other one is for monitoring. There's another third one, but it doesn't stay long. It just initializes the pod and then disappears away. So the monitoring container's job is to collect all the logs and relevant metrics and push them to the anypoint control plane. So basically it acts as a sidecar, or you can say it is a helper container. So in such scenarios you can have multiple containers in a single pod, but usually if we see normal applications, they will go by one pod, one container per pod. Now, The other way around is also possible. A node can have multiple pods as well. The way a pod can have multiple containers, a node may also have multiple pods. Now, a pod on node A might want to communicate with the pod on node B, or maybe two pods on the same node might want to communicate with each other, or there could be an external agent who wants to communicate with the pods. When it's external, what I mean to say, it's outside the Kubernetes cluster. So, how do we facilitate this communication? Now, this in Kubernetes is done with the help of services. So, let's explore services. So, the first service in the list is the node port service. But before we try to understand this node port service, we need to understand a few basic things about networking in Kubernetes. Now we all know that node is a physical or maybe a virtual machine. Let's assume it is a physical machine for the sake of simplicity. So if the machines need to talk to each other, they need to be a part of network, and only then they can form a cluster, right? So they have to be part of a network. So how can they form a network? They basically connect to each other via routers or switches. So let's introduce one router. Now this router has an IP address of 192.168.0.1, and it connects this node and the other node. Now both the node have been leased an IP from the router. Now let's add one more participant, which is an external machine, and that's not part of this cluster. Now you might be thinking that as all both the nodes are part of the same network, can't they be part of the cluster? Now cluster and network is a bit different thing. You can have all the machines in one network, but it's not necessary that all the machines could be part of a single cluster, right? So when I talk about cluster, these two nodes are aware of each other, and they both together are orchestrating some functionality. For example, we know, right, that there is a leader and a follower mechanism. So the leader is orchestrating with the worker nodes. In case if the leader goes down, then the nodes are capable of gathering over a consensus and deciding upon a new leader. So basically, these nodes are aware of each other, and they can take actions accordingly. But this machine, on the other hand, it's part of the same network, but it doesn't deal with these nodes on time to time basis. Only if you try to send a request on this particular IP address, only then will it try to connect with the node. But as such, it's not at all aware of these nodes in the network. Okay, so that's about the node network. But a node also has pod in it, and the pod has container. Okay, so now we know that the container was brought to have its own isolated set of resources like disk, RAM, and even network, right? So the container will basically have its own network. But since in Kubernetes the container is wrapped inside a pod, the container has to share the network of pod. So always remember, if a pod has multiple containers in it, it always shares the network of pod. So if you put two containers in one pod listening on port 8080, there will definitely be a port conflict despite the fact that we know a container has isolated resources. But in Kubernetes, if a container is inside a pod, it shares a network of pod. So basically, a pod's IP address is assigned to container. So if a pod has two containers listening on the same port, there will be port conflict. Now let's see how the network for pod is there in Kubernetes. Now same thing, the pod will have its own network, and in Kubernetes, the networking is a plugin. You can install a plugin. So There are multiple vendors out there like Calico, Flannel, etc. And they will help to provide the container networking interface using which the pods can talk to each other. So I'm not going to go into the details, but just a basic overview of that. So this pods will have their own virtual network. They won't be using the network of this physical router, but instead they'll have their own virtual network. So assume this to be a virtual router and it's leasing out two IP address 10.0.0.2 and 10.0.0.3 to the other node. Okay, other pod. So both the pods have different IP addresses. So what we observe that the pod network is different than the node network, and this pod can easily communicate to each other using this IP address. Now assume that we have APIs hosted in both the pods on the first and the second node, and someone outside the cluster, for example, this machine, wants to access the APIs. Now, since pods are creating their own network, this machine cannot directly access those pod because despite the fact that this machine is on the same network as of both the nodes, it still cannot access the pods. The reason is that the virtual network that has been created for the pods, it is a part of Kubernetes, the container networking interface which has provisioned this network, which is this router for demonstration purpose. Now that container network interface has been given by Kubernetes, or we have installed that plugin. Now, since both of these nodes are part of the Kubernetes cluster, they can easily access the pods using that IP address because the this virtual network is part of the cluster and this machine is not a part of the cluster. Hence, it cannot directly access the pods using the pod IP address. For example, 10.0.0.2, if this agent or this machine tries to access this IP, it will definitely fail. So how does this agent get access? Now, one of the option would be that to log into this node, maybe do a remote desktop, maybe do an SSH into one of the nodes. Basically, get inside the cluster and then run a curl command or use any agent to call. But that's not what we want, right? We want this agent to directly access using some IP address or something, not by logging into one of the nodes. So this is where the node port service comes into picture. So let's understand that. So here's how the node port service works. I have simplified the diagram a bit just to clear the clutter so that we understand it better. So the idea here is to forward a port on the node to the pod or eventually the Docker container. Now, why do we do this? It's simple because the node and the agent, which is the laptop in this case, are both on the same network, which means that this laptop can easily access the node but cannot access the container. So, what we basically do is we forward the port. So, here in this case, the port 30,008 is being forwarded to the port container or the pod's port 80. So basically, the agent will call the IP address of the node and call on port 30,008 because that is what we configured. Now that port will be specifically being listened by the service, which is the node port service. And then the node port service will realize, okay, there is a mapping. I need to forward this traffic to the pod with IP address 10.0.0.2 on port 80, and that is how it works. So this is what you can see. 192.168.0.5 with 30,008 gets converted to 10.0.0.2 colon 80. So this is how the port forwarding works. Now the same concept can be applied in case of multiple pods. So there could be scenarios where one single node will have multiple pods on it. So even in that case, the service will basically, this node port service can also behave as a load balancer because it can call any of the pod, right, randomly, because there are two pods with which have the same. So basically this pod has a replica, and the node port service can easily balance or randomly assign the request to any of the uh, replicas. And this also can be extended to multiple nodes. So there could be situation when there could be more than one node, and the container which is having the same app, so replicas can be scattered across multiple nodes. Even in that case, this single service is always extended across all the nodes in the cluster. So node port service can also do some sort of load balancing across the different pods. Next up is the cluster IP service. Now take this example. Here app 1 wants to communicate with app 2. There is an API hosted on app 2 which needs to be called. So to make a call, app 1 needs to use the IP address of app 2, right? This is the pod IP address. And same is the case with app 1. If app 2 has to communicate with app 1, it has to use a pod IP address of app 1. Now that looks fine. We can use these IP addresses to call the other pods. But what if the pod crashes? So in that case, that pod is gone. So the app2 is not anymore. But since Kubernetes has the replication controller, it will always try to maintain the desired number of pods for a given application. So it will spin up a new container. But the problem is that once the new container comes up, once the new pod comes up, it will have a different IP address, a different pod IP address. So if you have used a pod IP address of 10.0.0.3, it's not working anymore, right? Because now it's 10.0.0.5. So to solve this problem, there is a component called as cluster IP service. Now the cluster IP service will be per pod. So if you see in this diagram, app 1 has its own cluster IP service and app 2 has its own cluster IP service. Now the idea behind this cluster IP service is to have a static IP assigned. So the pod will always have a static IP assigned like 10.0.0.8, and pod with app2 will have 10.0.0.9. So in the event the pod crashes, for sure the IP address, the pod IP address will change, but the cluster IP address would always remain the same. So in that case, now if app1 has to call app2, it can use the cluster IP address which is 10.0.0.9 and be rest assured that the call will be successful even in case the pod crashes. So that's the idea of the cluster IP service. Now let's look at a slightly different flavor. So here is an app 1. Again, there are four replicas of app 1 which are scaled across multiple nodes. So it's in this node 1 has two replicas and node 2 has two replicas. So like I said, each app or each pod has a cluster IP service. But If the pod has multiple replica, if it's the same pod with multiple replica, the cluster IP service would be shared among them, as is in this case. So pod with app1 has 4 replicas, but the cluster IP service remains the same. And the cluster IP service can again load balance among all the pods. Similarly, the second example, the app2 is scaled uh, across 2 nodes with 4 replicas, and it also has a cluster IP of 10.0.0.12. So to sum it up, cluster IP service basically provides us with a static IP so that even if the replica of a particular pod goes down, we still have an IP which can route the request properly. Now, there is a problem in this case. It's that you cannot define the IP address, or the IP addresses are just not good to remember, right? So assume that you are trying to deploy an application, and in the property file, you're not going to write the IP, but you'd rather like to use a fully qualified domain name to access the applications, right? So that also can be done, and there is a format using which you can access. So here's the format. So it's like app name. Now this is particularly specific to runtime fabric. So this has app name dot namespace dot svc dot cluster dot local. Now cluster dot local is the root domain. SVC stands for service. Now there are multiple options available. You can also there is an option of pod default, but that's beyond the scope of this video. What we can use, or what is being used in RTF, we mainly used svc.cluster.local, and then the app name and the namespace. So this FQDN will basically help us to the DNS resolver will resolve it into the cluster IP service, which is a static IP, and we can use it directly. But what is this namespace in here? Let's try to understand what exactly is namespace. So namespace is basically a logical grouping of pods. Take this example. We have our API-led connectivity model. So we have experience, process, and system. Now there could be multiple APIs, but they can be grouped under a certain criteria, right? Like certain set of APIs belong to the system layer. So it makes sense to group them into a namespace so that Kubernetes can manage them, or if there is a Kubernetes administrator, he can do all sorts of manipulations or modifications, whatever is required. So for easier management, it makes sense to logically group the pods. So the same is the case here. We group the pods. So this pods, now this could be completely different APIs, but since they belong to the experience layer, they are added in the experience namespace. Similarly for process and system. It's not necessary that we go by this convention. There could be other options also, like some could be backend, right? Some could be database. So you can add database namespace. So this namespace are in Kubernetes ideally can be configured. But coming to RTF, uh, this is the format which we have seen in the last slide, where we saw the fully qualified domain name was app name dot namespace dot svc dot cluster dot local. So that namespace is basically the org id. So any applications that we deploy will fall under a namespace of your org id, and using that we can segregate the pods, and Kubernetes can manage them accordingly. But if it's a plain Kubernetes, if we remove that RTF part, this namespace is configurable. We can configure on our own, and things work accordingly. So that's about namespaces. Now let's move to the load balancer service. To understand this service, let me bring up the node port service diagram. So here's the diagram. Now we have seen that in node port service, if some person wants to access the service and he is outside the cluster, he can basically leverage the node port service. So it opens a port on the node in which the pod is running, right? And that was quite a good option. But there are certain drawbacks of this approach. First drawback is that assume someone outside your network, let alone the Kubernetes cluster. Now, these machines are inside one network, but you ideally want to expose this as front-end application, maybe web UIs. So you would basically like to expose this over the internet so that anyone across the globe can access your service. So you cannot leave such ports open like 30,008, and because this is basically a loophole, you're allowing this, which is not a standard port, and you're directly exposing your Kubernetes cluster node which has pods in it. So basically it's a security risk to open up a node which has multiple pods and containers. Anyone getting hold of this port can try to attack and maybe bring the whole node down, which is a very critical part of the Kubernetes cluster. The another problem is that uh, anyone over the internet or any external consumer might not want to add the port, right? So whenever you try to access a web page or an API, usually don't add a port, because for HTTP it's 80 and for HTTPS it's 443. That's implied. That gets automatically added even if you don't add it. So no one's going to add the port. All the user wants is uh, some name, right? Fully qualified domain name to access it. So no one's going to write the IP address or the port number. So that's yet another drawback, that we don't want to go with the IP address or the port number. So basically, we want some element that can take care of both the things, right? So the IP address can be handled by a DNS server. It could be a public DNS or your internal DNS. If you want to access within your own network, then an internal DNS might work. But if not, then you get a public IP, add a DNS entry on the public DNS servers. And only port 80 and 443 should be exposed, no other ports, because even if you see at a production scenarios, your Kubernetes cluster or any cluster or any network which is internal, the firewall is there, and the firewall only exposes a limited set of ports. For example, 80, 443, or 23 for SSH access, right? So we would want to only expose certain ports and not ports like 30,008. Now here the port that I've used 30,008, it's because the node port surface uh, has a range and it starts from 30,000. All right. So now we are aware of the problem that we need to fix, and load balancer is one such component that can help us to achieve the same thing. Okay. So let's see how it works. So now we introduce a new service which is called as a load balancer service. So the load balancer service would basically spin up a virtual machine. If it's your on-prem cluster which you manage on your own, in that case you have to provision a VM and you have to introduce a load balancer into the cluster and that will take care of. So this load balancer can have a public IP address and it can open up port 80 and 443, and then it will do translation to the node port service. So node port service will still be there. It's just that a load balancer service acts as a proxy between the two. So now we have the load balancer service. Now, if you are using managed services like Amazon's Elastic Kubernetes service or Azure's Kubernetes service or Google's GKE, in that case, they will use their native load balancer and you will be charged accordingly. So native load balancers will be the layer 4 load balancer, basically working on the TCP and IP layer. They just forward the raw traffic. They cannot read anything. They just blindly forward the traffic. So all the Forwarding thing would be done by this LB service. So now what we have done, we have got rid of exposing this unwanted port externally. Now we can only expose port 80 or port 443 that we want. And additionally, this load balancer service can have a public IP, and that public IP can get a DNS resolved name. Okay, so now the flow becomes like this. The request from any external machine which is outside the cluster, or it could be even outside your network, can use this fully qualified domain name, and then the request reaches out to the LB service, and then from the LB service it goes to the node port service, and from the node port service the original flow remains the same. Now we know about the node port service. So if you observe, this LB service is nothing but an extension of a node port service. So if you create an LB service, behind the scenes there would be a node port service supporting it. And same is the case of cluster IP service. This node port service will internally use cluster IP service. So the flow is like cluster IP, then the node port, and the load balancer service. So here's the extended version of the previous slide. Now I have clubbed all the concepts of services that we have learned so far: cluster IP, node port, and load balancer service. So in this diagram, I have an app which is scaled across two pods. So basically these are two replicas of the same application, and we are trying to expose them externally. So as we have seen, we can create a load balancer service which sits outside the nodes. So depending on what cloud provider you use, it would be native to that cloud provider, or if it is on-prem, you have to spin up a new instance for a load balancer and install it. So if it is EKS, then it's Amazon's network load balancer, and so on for other providers. So we see that this load balancer, now depending on your requirement, it can have a public IP or a private IP. If it's expected to expose to some over the internet, it needs to have a public IP address. So a client tries to access that service. So it will basically use the fully qualified domain name, go to the DNS, get the IP address. Now the IP address is retrieved, and since it is HTTP, it will route request on port 80 of the load balancer service. Request comes to the load balancer. Now obviously load balancer has to reach the node. Now it will have both the nodes registered. So it will, based on the algorithm it has, it will choose one of the node, and we need to access this node, right? So it will reach out to the node port service. Now we have seen that a node port service will expose a port on the node from the range 30,000. So here we can see it's 30,008 port, which is exposed on both the node by the node port service. Observe that node port service is available on the nodes, and it's scaled across both the nodes. So the request comes to the node port. So this is the IP address of the node that has been selected, and the port. So comes to this node. Now the node port will route forward to the cluster IP because it eventually has to reach the pod, and this is the IP address of the pod. So again, it sees if there are multiple nodes on it on this, if there are multiple pods on the node, then it, based on its logic algorithm balancing, it will select any of one of them, but in this case we just have one pod. So it takes that IP 10.0.0.2 port 80 and eventually forwards that traffic to this particular pod. So this is how the overall flow of the load balancer service works. So eventually cluster IP is the main thing. It gives static IPs for the pods to communicate, and that static IP would be the cluster IP will have its own IP, and cluster IP will forward that uh, to the changing IP addresses of the pods. So basically this 10.0.2 I've shown is for demonstration purpose. It eventually goes to here, but this cluster IP might have some different IP address. So it could be like 10.0.0.4, and that would convert to 10.0.0.2. So cluster IP, then node port and load balancer service. So all these three components together enable communication between the pods in a Kubernetes cluster. Now there are a couple of limitations to this approach. Let's try to understand them in the next slide. So in this slide, I have tried to simplify the diagram and have made some modifications. Let's try to understand it. So here are pods. I have total four replicas of the order. Let's call it as an order microservice. Okay, which it has four replicas, and this is basically a pod. So four replicas of the orders microservice. And I have another application which is the accounts microservice. Again, it has four pods, which is four replicas. Now, if I create services for accounts and order, so basically I'll have two services, right, for each of them. So I can create a node port service. I can create a cluster IP. First of all, I'll have to create a cluster IP service so that I get a static IP address for orders and accounts. So we have a node port for external access, cluster IP for internal access. Now let's move to the load balancer. So we create a load balancer. Now observe that there is some change here. Now this load balancer is for orders and the other one is for accounts. Now I ended up creating two load balancers. But why do I have to create two load balancers? So the problem here is that when you create a load balancer in as a service on any managed service like Google Kubernetes engine or maybe AWS EKS, right? In that case, the cloud provider will facilitate a network load balancer which is native to their platform. So this network load balancer is a layer 4 load balancer, which means that it works only with the TCP IP packets. It it it's not smart enough to understand the contents of the request and route it to a particular endpoint. So basically, it will get your request and forward to a particular IP address. So it will have, for example, it has two nodes registered to itself, right? So it based on the IP address of that node, it will choose any one of them and forward it. It cannot read the contents of your request. So owing to those reasons, we we cannot have any routing rules written in this particular load balancer. It can only route packets based on the IP addresses. So that is why for each type of microservice which has multiple replicas, we end up creating one single load balancer. Now this load balancer have cost associated with it, right? So if you use on AWS EKS, they'll provide you an network load balancer and you will be charged for it. So if there are hundreds of microservice, you end up creating 100 network load balancer, which in no way is an efficient solution, right? So basically, uh, we don't want this option. But now if we go with this option, how will be the flow? The same as earlier, right? We now create a load balancer specifically for orders. So I've just changed the URL, LB service orders, and then I get the IP and the same old flow. Similarly for accounts, I have the same flow, and then it's the request is served or the access is granted. Okay, but as we realize that this approach is not good because we end up creating multiple network load balancer. So it would be a better approach if we could condense this two load balancer into one, which means that we want a load balancer to be smart, and rather than creating one specific domain, we can have something like this. So, so this is an approach, right? We have the same domain, but the resources changes. For example, if the resources orders, we move or we route it to the orders pods. If the resource is accounts, we move it to the accounts pods. So to cater to this requirement, we have something called as Ingress. Now, Ingress can behave as a layer 7 load balancer, which is a smart load balancer. You can basically read your request, do TLS termination, and also it gives you an ability to do URL mapping. So that is what helps us to overcome the load balancer service limitations. So now the idea behind having an ingress is that we want a layer 7 load balancer, which basically is smart enough to understand the traffic. It can read above the TCP packets. It can basically understand a protocol. It can do TLS termination, and it can also do load balancing and URL routing based on the resources that have been used. So we want this feature. The layer 4 load balancer, which is being created using the service, doesn't fulfill this requirement, due to which we have to create multiple load balancer for each microservice. So to do that, we would basically need to deploy an application, right? So it could be an Nginx load balancer, HA proxy, and traffic. So this they provide solutions. We can basically take that solution and deploy it. So now this particular part in the ingress is known as ingress controller, because it usually does all the task of controlling. But alone, the controller is not enough. It needs to have some configuration, like right, like having rules how to route based on the path, right? So that can be done at the resource. So where we have rules defined, like if it is /accounts, push it to the node port 3 listening on 32008. If it's order, push it on service node port service on 32009. So this is handled by ingress resource. So any configuration is done on the ingress resource, and it's then implemented by the controller. Think of it as this is an interface which defines the rules, and controller is how you implement the rule. By default, Kubernetes doesn't come with a controller. You have to deploy your own controller solution, or in case if you're using a managed Kubernetes service, there are many native options available out of the box in that case. And both of this resource together create an ingress. So ingress is basically ingress controller along with ingress resource. Now this would certainly help us get rid of the first problem, that we don't need to create multiple load balancer for multiple microservices. We can just have one layer 7 load balancer, and it can route based on the resource, right, accounts and orders. Plus we have a single point where we can configure the TLS termination, which means that we don't need to have TLS configured on each application, right? And that helps enormously from maintenance perspective, because the admin would not want a developer to implement TLS on all its application, right? There are two reasons. One is that it would unnecessarily make things complicated, because each app will have TLS termination. And first of all, you cannot have a load balancer. You would not have want to have a load balancer without TLS. So if you implement a TLS at load balancer, and the developer also implements TLS in his application, there are two TLS termination happening, which would increase the latency. And you would want to have only one TLS assigned certificate. So it would be it would be helpful to have only one TLS termination at a load balancer level, so that any Kubernetes administrator can just change it based on the requirement. So it can get expired, or whatever reasons maybe, there's a single point where he can change rather than going to each application. And the other thing is that since it's Nginx, HA proxy, and traffic, these are load balancing products, so it gives you load balancing ability. So that is how an ingress in Kubernetes is created. So it's basically controller and resource. Now back in the LB service limitations diagram, we can replace the network load balancer or the load balancer service with our application load balancer, which is Ingress. So here we replace both the load balancer service using an Ingress. Now this Ingress can help us support TLS as well as load balancing, and the important thing, it's smart enough to route the request to a particular service and eventually to a pod. So now what would happen is we will change this domain. Now this would be a generic domain, so it's LB service devnet, and then the resource where we want to route. So in this case, it's order. Same thing, we will get the IP address and then the request would be this is the DNS translation of domain, and this is how the request would eventually make it to the ingress. Same applies to the accounts. So now accounts is a part of the URI param, and then same would happen to the DNS resolution. We get the IP. Now both of them are basically calling the same public IP address. We got rid of two load balancer. It's just one load balancer. So that is how Ingress helps us to overcome the limitation of a load balancer service, and it's quite effective when compared to its counterpart. So now let's sum things up. So we have three service. Ignore this. This is not a service, but I didn't have any option to place it, so I just added in this table. But we have three main services, and cluster IP is the root. First of all, when you will deploy a pod, a cluster IP service has to be created, and its job is to give a static IP interface for pods. So this service will have one IP address, and that IP address can be routed to multiple pods. So it gives you a static IP. And the access type for this is internal. So any communication which has to happen from one pod to the other, irrespective of the fact that it is on node A or node B, as long as it's in the same Kubernetes cluster, it can use cluster IP to access. Next is node port service. So it does basically port forwarding, forwards a port on the node, basically exposing a port on the node so that someone outside the cluster can call, and that node port will call this node port service. Node port service will call cluster IP because it has to call a certain IP, and that cluster IP will redirect it to a particular pod. So node port again is an extension of cluster IP, and it caters to any external traffic. Now, the problem with node port was that you are directly exposing the port on a node, where and you don't want your clients to specifically specify a port. If it is a REST API, all they have to just give is maybe an IP address, or if not that, then give a fully qualified domain name, and then they should have a page or any API response ready. So to get away with all those complexity, we have a load balancer service, and it's basically a network load balancer which works on layer 4, isn't smart enough to route traffic based on the URL mappings, and it caters to only external access. Now Ingress, it's not a service, it's basically a different component that doesn't come by default on Kubernetes. You need to deploy an Ingress controller so that your Ingress resources can be implemented in that controller. So Ingress again overcomes the limitation of a load balancer type service, and it's a layer 7 application load balancer which is smart enough to do TLS termination. It can do routing based on the URL specified, and also load balancing. Again, its job is to cater any external communication. So any external traffic that wants to uh, leverage the resources which are present in cluster or get a response from them. In that case, we use Ingress. So that completes our Kubernetes basics. Now, I have only covered the basic level. Now, you won't be working on all these concepts on a day-to-day basis. If you're working on RTF, you won't get a direct hands-on on this. But yes, it's quite important to understand these things because eventually behind the scene this is all what takes place. So if you understand this concepts clearly, you would be able to figure out the communication that's happening in the pods. All of these components have configurations which are automatically done by runtime fabric. We don't have to do it, but it's just that having a basic idea or understanding is great because that helps you troubleshoot issues. And also for Ingress, if it's self-managed Kubernetes. So if you are deploying your Kubernetes RTF on EKS, GKE, or Azure Kubernetes service, in that case, Ingress has to be configured separately. But if it is an appliance, in that case, you don't need to do much of a configuration. Basically, you don't need to write any YAML file. You can just do that configuration on the UI by just uploading the certificate. So that's all for this video. I hope you found the video useful. Thanks for watching.